In many ways, the physical world feels predictable. We are not surprised when a ball falls under the effect of gravity, and we are not surprised when the impact of an object depends on how fast it is moving. Many physical phenomena follow patterns that feel almost natural to us. But the theory introduced by Einstein at the beginning of the 20th century was not one of those examples. Special relativity was born during a deep crisis in physics, and it forced scientists to rethink one of the most basic ideas we use to describe reality: time. For centuries, time had been treated as something absolute, a universal background, something that flows in the same way for everyone everywhere. The motion of objects could change depending on the observer, but time itself seemed untouchable. Then, between the 19th and 20th centuries, the study of electromagnetism revealed something unexpected. Maxwell's equations showed that light is an electromagnetic wave and that in vacuum it travels at a fixed speed, c. But this created a problem. In ordinary life, velocities depend on the observer. If you walk inside a train moving at 100 kilometers per hour and you walk forward at 10 kilometers per hour, someone standing outside the train would say that your speed is 110 kilometers per hour. This is how motion normally works. Velocities add. But light does not behave like an ordinary object. No matter how the source moves, every inertial observer measures the same speed of light in vacuum. Always c. This was deeply strange. How can a speed be the same for everyone? How can something not depend on the reference frame from which it is measured? Many ideas were proposed to solve this problem, but Einstein's solution was the most radical. Instead of changing the speed of light, he changed our idea of space and time. If the speed of light cannot change from one observer to another, then something else must change instead. And that something is time. To understand why, we need to enter the world of special relativity. To solve this problem, Einstein proposed two principles. The first one is the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial frame is a frame that is not accelerating. It can be at rest, or it can move in a straight line at constant velocity. This means that there is no privileged frame of reference. There is no special observer for whom the laws of physics are more true than for everyone else. Different observers may measure different values. They may disagree on positions, velocities, distances, or even time intervals. But the relationships between physical quantities, the laws themselves, must keep the same form. The second principle is the constancy of the speed of light. Every inertial observer measures the same speed of light in vacuum, c. This is the radical step. Einstein accepted that the speed of light does not adapt to the observer. It stays the same. So if the speed of light cannot change from one reference frame to another, then something else must change instead. And that something is our measurement of space and time. In special relativity, space and time are no longer two completely separate backgrounds. They are linked together into a single structure, space-time. To understand what this really means, let us use one of the simplest thought experiments in special relativity: a light clock. A light clock is made of two mirrors facing each other, separated by a distance L. A pulse of light bounces between the two mirrors. Now, imagine that this clock is inside a spacecraft and that an astronaut is floating next to it. For the astronaut, the light clock is at rest. The astronaut sees the light travel from one mirror to the other, covering a distance L. Then the light comes back, covering the same distance again. Because the speed of light is constant, the two parts of the motion take the same amount of time. So, during one complete tick of the clock, the light travels a total distance of 2L. If the total time measured by the astronaut is delta tau, then we can write c equals 2L divided by delta tau. This delta tau is called the proper time. It is the time measured in the reference frame where the clock is at rest. Now let us observe the same light clock from another inertial frame. This time, the spacecraft is moving horizontally with velocity v. From this external point of view, the clock is no longer at rest. It is moving. So, while the light travels upward and downward between the mirrors, the entire spacecraft also moves horizontally. This means that the vertical path seen by the astronaut becomes a diagonal path for the external observer. The motion of the light and the motion of the spacecraft combine, and the path followed by the light becomes longer. but the speed of light is still c. It cannot become larger to compensate for the longer distance. So if the light covers a longer path while moving at the same speed, then the measured time must become longer. We call this time delta t. And this is the key idea. The astronaut measures delta tau. The external observer measures delta t. The physical clock is the same. The light is the same. The speed of light is the same. But the measured time interval is different. This is time dilation. A moving light clock ticks more slowly when measured from another inertial frame, not because the clock is broken, but because light must cover a longer path while still moving at the same speed. Now let us look at the mathematics behind this phenomenon. To do this clearly, we need to keep two quantities in mind. The first one is c. This is the speed of light, and it is constant. The second one is v. This is the velocity of the spacecraft, moving horizontally with respect to the external observer. And we also need one simple idea. Speed is distance divided by time. Equivalently, distance is speed multiplied by time. We can summarize the geometry of the light clock using a right triangle. The vertical side of this triangle is the distance between the two mirrors. That distance is L. From the astronaut's point of view, the light travels a total distance of 2L during one complete tick. So we have c equals 2L divided by delta tau. If we isolate 2L, we get 2L equals c times delta tau. And if we study only half of the tick, the vertical distance becomes L equals c times delta tau divided by 2. Now let us look at the horizontal side of the triangle. This side is produced by the motion of the spacecraft as seen by the external observer. The spacecraft moves with velocity v, and during half of the tick, the time measured by the external observer is delta t divided by 2, so the horizontal distance is v times delta t divided by 2. Finally, the hypotenuse represents the path followed by the light from the external observer's point of view. The light still moves with speed c, and during half of the tick, the external observer measures a time delta t divided by 2. So the length of the diagonal path is c times delta t divided by 2. Now we can apply the Pythagorean theorem. The hypotenuse squared is equal to the sum of the squares of the two sides. So we get c times delta t divided by 2 all squared equals c times delta tau divided by 2 all squared plus v times delta t divided by 2 all squared. Multiplying everything by 4, we remove the denominators. So we obtain c squared times delta t squared equals c squared times delta tau squared plus v squared times delta t squared. Now we bring the terms containing delta t squared to the same side. Then we factor out delta t squared. And finally, we divide by c squared minus v squared. This gives us delta t squared equals c squared divided by open parenthesis c squared minus v squared close parenthesis times delta tau squared. At this point, we rewrite the denominator in a more useful form. Substituting this expression and simplifying c squared, we get delta t squared equals 1 divided by 1 minus v squared divided by c squared times delta tau squared. Finally, we take the square root of both sides, and we arrive at the formula delta t equals 1 divided by the square root of 1 minus v squared divided by c squared times delta tau. This is the mathematical form of time dilation. The quantity multiplying delta tau is usually called gamma. Now let us look at gamma, because gamma tells us how strong the effect really is. If v is equal to 0, then the ratio between v and c is 0. So gamma becomes equal to 1. And if gamma is equal to 1, then delta t is equal to delta tau. This means that there is no difference between the two measured time intervals. Both observers agree on the time. But if v is not equal to 0, then gamma becomes greater than 1. And if gamma is greater than 1, then delta t becomes greater than delta tau. This is time dilation. In this setup, the astronaut measures the proper time delta tau. For the astronaut, the light clock ticks normally, but the external observer sees the spacecraft moving. And from that external reference frame, the same clock takes a longer time to complete one tick. So the disagreement appears when two different reference frames compare their measurements. The faster the spacecraft moves, the stronger the effect becomes. And if v gets closer to the speed of light, gamma grows enormously. In the limit, gamma tends toward infinity. This is one of the reasons why no physical object with mass can reach or exceed the speed of light. But that is a topic for another video. Now, this formula also helps us answer an important question. If time is relative, does that mean that all the physics built before Einstein was wrong? And if it was wrong, why does it work so well? The answer is both yes and no. Yes, time is really relative. But at speeds much smaller than the speed of light, the effect is extremely small, and these are the speeds we deal with in everyday life. So, in everyday situations, gamma is almost equal to 1. For this reason, classical physics works perfectly well as an approximation. But when velocities become comparable to the speed of light, gamma can no longer be ignored. At that point, space and time must be treated relativistically. This is why special relativity feels so counterintuitive. Our everyday experience happens at speeds where time dilation is far too small for us to notice. So our intuition tells us that time should be absolute, but nature tells us otherwise. And this conclusion, expressed in such simple words, required centuries of physics to become clear. If you enjoyed this video, consider subscribing to the channel and leaving a like. Thanks for watching, and I will see you in the next video.